We present RiverState, a visual design for finite state machines that adopts the design of a Sankey diagram to depict the flow of state transitions. We work with our industry partner QPC Limited to explore a real-world dataset of call centre interactions. The purpose of this research is to explore how customers navigate through the call centre landscape and what impact the journey has on the customer experience. We identify 7 primary states a caller can exist in. The IVR is an automatic voice routing system. A queue event is when the caller is waiting to speak to an agent event is an instance of the caller speaking to an agent, and the hold event notes a temporary wait in the conversation whilst the agent processes a request or searches for further information. 2 additional agent states note one agent calling a second agent, and then the second agent joining the call with the customer. The final state signifies the call ending. The agent state can also be expanded into 10 different sub-states depending on the department the agent is working in. We present this finite state transition data through the RiverState application. Here, sequences of events are shown as flows from one axis state to the next. The vast majority of calls enter the call centre via the IVR, and then most transition into the queue. A large amount of calls, however, end before they are routed into a queue. Flows of calls from the hang-up state are from repeat calls by the same customer. We sequence calls together to explore higher order patterns. A primary challenge we had to overcome when visualising this dataset was that later time step transitions experience very low frequencies. Growing the transition edges only worked to a certain extent before the early time steps became occluded. Because of this, we implemented a variable maximum transition width which stops occlusion. When the maximum width is reached, the colour value for that axis increases instead. This means that later time step transitions can be explored whilst maintaining the context of the complete dataset. Additionally, the user can choose from 2 glyph types that represent the same value, thus freeing up the dimension of colour to be used to represent other values. These glyphs appear above and below each axis and scale in size according to how far beyond the fixed point that axis would have grown. The user can directly apply brushes to states by clicking on them. The default brush filters out all calls that do not pass through that state. Applying multiple brushes to the same time step applies an OR operator to the brush. Calls can pass through either state and will remain in focus. A user option flips the brush parameters to filter out all calls within the brush selections. This is useful to remove unwanted noise. Here we apply a brush to the queue state followed by the agent state. The second brushing feature enables the user to apply metadata filters through interface sliders. These metadata values typically involve durations at states or event counts. An important metadata variable is the NPS or Net Promoter Score value, which represents the customer feedback retrieved by text after the interaction. A score of -1 represents a no response. Here we apply a brush that filters out all non-response NPS calls. Remaining in focus is the cumulative journey of all callers who responded to the NPS survey. In order to explore the quantity of calls transitioning through these states, the user can hover the mouse over individual states to see the inflow and outflow of callers within that state. The size of the window can be adjusted to the user's preferences, as well as the axis labels. A limitation of the Sankey diagram is that the journey of specific calls in a state cannot be identified beyond one time step in either direction. We implement a journey tracing feature that highlights the path calls in a selected state to transition through and will transition through after that state. This help identifies trends in the data and provides further insight into the state transitions. Here we can see the complete customer journey of all callers who transition through this state. Additional features of the software enable the user to change the variable by which we map colour. Here we map the colour by the average wait time of the calls within that transition. You can observe that wait times are much higher for calls in the consult states. And also, as time progresses, you can see natural increase in wait times as the time step increases. The user can also adjust the scale of the colour map values to bring the mapping into a reasonable range. The user also has a selection of colour maps to choose from, including colourblind friendly options, sequential maps and divergent maps. Using these features, we present some interesting observations about our industry-provided call centre data. The first observation we make is that there is a distinct shift in pattern after the first 5 time steps. Whilst it's not initially visible, if we grow the transition edges, we can see this trend repeating continuously, slowly decreasing in frequency due to abandoned calls. This clear separation highlights these initial transitions as important. The latter pattern shows that calls revolve around the agent state, which is to be expected, but then in almost every time step, the state after that of an agent is most likely going to be a call end followed by a hold event, followed by another agent event, followed by a queue event. This pattern highlights the somewhat predictable nature of the journey. The call end state is made up of 2 segments: callers who ended the call and then called back, which is usually indicative of unresolved problems with the service, and then callers who ended the call and made no further interactions with the call centre. Using the Details on Demand feature, we can see that in the first 5 time steps, out of the almost 180,000 calls entering, more than half hang up before reaching the queue. Of those in the queue, the majority end up speaking to an agent. This shows that out of the 179,000 incoming calls, only 57,000, or 31%, end up speaking to an agent. It's also interesting to note that out of the initial 95,000 to abandon the call, 11,000 of those call back within the day. Here we can observe some interesting behaviour in the dataset. For example, we can see multiple sequential queue events, which is indicative of overflow queues being used during busy periods in the call centre. Now we want to explore the customer feedback metric. Firstly, we apply a metadata filter to show only calls who responded to the survey. If we colour the RiverState plot by the NPS score, we can see that the average score doesn't appear to vary by much. You can make out that early stage call ends have a somewhat positive effect on the outcome, but the trend can't be seen clearly. If we change the upper and lower range of the map from 0 to 10 to 4 to 7, we can see this effect more clearly. As we move along the plot, we can see that the more event transitions there are, the more likely lower score is to be given. It appears call duration has a major impact on the NPS score. If we apply a metadata brush to show a range of agent durations, low range agent duration appears to hold a relatively neutral NPS score. As we move the slider, we can see that the NPS score increases until a point and then begins to decrease again. This suggests that there is a sweet spot in the agent duration that optimises the NPS score. Any longer and they feel like time is wasted, and any shorter they feel the problem may not be fixed. Another strong predictor of NPS score is the wait time. The wait time strongly predicts the score given by the customer. Here we show the slider move along the wait time filter. Additionally, talking to more agents appears to have a negative impact on the NPS score. Here we filter the agents by event count. As we remove low agent count events, the NPS score quickly decreases. Thank you for watching.